Imagine you are holding a hot cup of coffee. You set it down and walk away. When you return an hour later, it is lukewarm. You have never, not once in your life, returned to find that cup hotter than when you left it. The coffee cools. The ice melts. The scrambled egg never unscrambles. You age. You do not grow younger. Memories form of the past, never of the future. These are not mere observations. They are the unyielding directives of a law so fundamental that it governs every process in the cosmos, the second law of thermodynamics. And woven into that law is the most profound mystery of physics, the arrow of time. Why does time have a direction? Why does it flow relentlessly forward and never backward? The answer, when you truly grasp it, is so strange and unsettling that it shook even Richard Feynman to his core. Let's start with what we mean by time's arrow. In our daily lives, past and future are unmistakably different. You remember yesterday. You do not remember tomorrow. A glass falls and shatters. The shards never spontaneously leap back together. These asymmetries feel obvious, but here is the shock. The fundamental laws of physics, the equations that govern particles, forces, and fields, are almost entirely reversible. If you filmed a single atom bouncing around and played that film backward, the reversed motion would obey the same physical laws perfectly. There is no timestamp in the equations of motion that says, this direction is forward, that direction is backward. At the microscopic level, the universe does not care which way time flows. So how does the irreversible emerge from the reversible? How does the one-way corridor of experienced time arise from laws that permit traffic in both directions? The answer lies not in the laws themselves, but in a quantity called entropy. Entropy is often described as disorder, but that word is too vague. A better way to think of it is in terms of arrangements or configurations. Consider a deck of cards fresh from the box, perfectly ordered by suit and rank. There is exactly one arrangement that matches that perfect order. Now shuffle the deck. The number of possible shuffled arrangements is astronomical, roughly 8 times 10 to the 67th power. If you define ordered as one specific sequence, then disorder is everything else. There are vastly more disordered states than ordered ones. Entropy is a measure of how many ways you can rearrange the components of a system while keeping its overall appearance the same. High entropy means many possible configurations. Low entropy means few. The second law of thermodynamics states that in an isolated system, entropy tends to increase. Not because there is a law forcing it, but because it is statistically overwhelmingly likely. If you start in a low entropy state, there are simply far more high entropy states to move into. It is not forbidden for entropy to decrease. It is just preposterously unlikely. Now apply this to the universe. The early universe, moments after the Big Bang, was in an extraordinarily low entropy state. It was hot and dense, yes, but remarkably smooth and uniform. Smoothness is low entropy because there are relatively few ways to arrange matter and energy uniformly compared to the chaotic, clumpy ways it could be distributed. As the universe expanded, gravity pulled matter together into stars, galaxies, and planets. Locally, this looks like order emerging. Stars are structured, not random clouds. But this is an illusion. The star burns fuel. It radiates energy into space as heat and light. That radiation disperses, spreading entropy into the surrounding cosmos. The total entropy of the universe increases. The star is a temporary island of local order, purchased at the cost of greater cosmic disorder. Every process you witness, every chemical reaction, every thought in your brain, every cooling cup of coffee, is a transaction in this grand entropic account. The universe is spending the low entropy endowment it received at its birth, and it is spending it irreversibly. Here is where it gets deeply strange. The arrow of time, the feeling that the future is different from the past, is not a fundamental property of time itself. It is a consequence of this entropic gradient. You perceive time flowing forward because entropy is increasing. Memory works in one direction because recording a memory is an entropy-increasing process. Your brain encodes patterns, and those patterns degrade and evolve forward in time. The past is fixed because it is the low entropy state from which we emerged. The future is open because it is the space of higher entropy states we are statistically moving toward. Time's arrow is not written into the fabric of spacetime. It is written into the initial conditions of the universe. This realization troubled some of the greatest minds in physics, and Richard Feynman was no exception. Feynman, with his unrelenting intellectual honesty, recognized the profound puzzle here. If the laws of physics are reversible and entropy increase is just statistical, then in principle, the universe could have started in a high entropy state. In such a universe, there would be no clear arrow of time. Events would be statistically symmetric in both temporal directions, but our universe did not start that way. It started with incredibly low entropy. Why? This is not a question the second law answers. The second law tells us that entropy will increase. It does not tell us why it was low to begin with. That initial low entropy state is an unexplained cosmic gift, and it is the bedrock on which the directionality of all our experience rests. Feynman called this the most profound mystery, and he was not exaggerating. The question shifts from why does time move forward to why was the universe born in such an improbable, finely tuned, low entropy state? One possibility is that it is simply a brute fact. The universe began that way, and we are here to ask the question precisely because that beginning allowed structures, stars, planets, and life to form. This is the anthropic principle. We observe a low entropy past because only in such a universe could observers exist. But this feels unsatisfying. It does not explain. It merely acknowledges. Another line of thought involves cosmology and the role of gravity. Gravity is strange. Unlike gases in a box, which reach maximum entropy when evenly spread out, gravitational systems reach higher entropy by clumping together. A universe with matter evenly distributed is low entropy from gravity's perspective. As matter clumps into stars and black holes, entropy increases. Some physicists propose that the early universe's smoothness, driven by a process like cosmic inflation, set the stage for this gravitational entropy journey. Inflation stretched quantum fluctuations into the seeds of galaxies, creating a smooth, low gravitational entropy canvas that gravity has been sculpting ever since. But inflation itself requires specific initial conditions. We have pushed the mystery back, not solved it. There is an even more radical idea. What if our universe is not alone? What if it is one bubble in an eternally inflating multiverse, where different regions have different initial conditions? In some bubbles, entropy starts high and stays high. Nothing interesting happens there. In others, like ours, entropy starts low. We find ourselves in a low entropy bubble not by design, but by selection. Only such regions permit the complexity necessary for life and consciousness. This is speculative, but it highlights how deep the problem runs. The arrow of time. This everyday asymmetry we take for granted traces back to the most foundational questions about the cosmos itself, questions about initial conditions, the nature of the Big Bang, and perhaps the existence of realities beyond our observable universe. Feynman also grappled with time's arrow in the quantum realm. Quantum mechanics, the theory governing particles at the smallest scales, introduces another layer of strangeness. The equations of quantum mechanics are also time reversible. A particle's wave function evolves forward and backward in time with equal legitimacy. Yet when we measure a quantum system, it collapses from a superposition of states into one definite outcome. This collapse, this moment of measurement, introduces an asymmetry. Before measurement, the future is a cloud of probabilities. After measurement, the past is a single recorded fact. Some interpretations of quantum mechanics try to eliminate this asymmetry by treating measurement as just another physical interaction with no special collapse. Others embrace it, suggesting that observation itself breaks time symmetry. Feynman, ever the pragmatist, focused on what could be calculated and tested. He developed the path integral formulation, where a particle explores all possible paths through spacetime, and the observed outcome is the sum of contributions from all these paths. Fascinatingly, this formulation is perfectly time-symmetric in its mathematics. You can run it forward or backward, yet the world we measure is not. The asymmetry once again comes not from the laws, but from the boundary conditions, the initial state of the system, and the nature of the measuring apparatus, which itself is a macroscopic, high-entropy object obeying the second law. Consider the disturbing implications. If the fundamental laws are reversible, then for every process you observe running forward, there is a mathematically valid reversed process. A broken glass reassembling, a person growing younger, smoke converging into a flame. These are not forbidden by physics. They are merely statistically impossible, given the low entropy past. If you could prepare the exact microscopic state, every atom and photon precisely reversed in momentum, the process would run backward perfectly. The universe does not prohibit it. Probability does. The chance of randomly encountering such a finely tuned reversed state is so infinitesimally small that it will never happen in the observable universe's lifetime. Time's forward march is a statistical juggernaut, not an absolute decree. This leads to a profound and unsettling thought. Your sense of now, of the present moment, is an illusion sculpted by entropy. Physics does not distinguish a special now. Einstein's relativity even shows that simultaneity is relative. Events that are now for you may be past or future for someone moving relative to you. The equations treat time as just another dimension, a coordinate like space. The flow of time, the sensation that the present is uniquely real and moving, is not in the physics. It is in you, in the thermodynamic arrow encoded in your brain's evolving states, in the accumulation of memories, in the irreversible firing of neurons. You are a complex dissipative structure, maintaining local order by exporting entropy to your surroundings. And that process creates the subjective experience of time passing. Without entropy increase, there would be no memory, no causation, no narrative of before and after. There would only be a static four-dimensional spacetime, a frozen block universe where every moment exists eternally. Feynman found this both beautiful and deeply mysterious. He marveled at how the directionality of time, so visceral and unavoidable in experience, is absent from the fundamental laws yet emerges inexorably from the statistical behavior of matter. He was shocked, not in the sense of being horrified, but in the sense of intellectual awe, at the realization that the flow of time is not a given. It is a consequence, a derived phenomenon resting on the improbable initialization of the cosmos. And the ultimate why of that initialization remains one of the great unanswered questions. We can describe how entropy shapes time's arrow with exquisite precision. We can calculate, predict, and harness it in engines and refrigerators. But the origin of the low entropy beginning is still wrapped in mystery. It touches on the birth of the universe, the nature of quantum gravity, and perhaps the very meaning of existence. So when you watch that coffee cool, or notice a wrinkle that was not there yesterday, or remember a conversation from last week, you are witnessing the arrow of time in action. You are experiencing the universe's long, slow, irreversible slide from the extraordinary improbability of its low entropy birth toward the featureless equilibrium of maximum entropy. The heat death. Trillions of years hence, when all stars have burned out, all black holes have evaporated, and all gradients have vanished. In that distant future, there will be no arrow, no past or future, just a timeless, unchanging sameness. But for now, we live in the universe's youth, in the afterglow of creation, surfing the wave of increasing entropy, and that wave carries us forward through time. The answer to why time moves forward is this. It moves forward because the universe started in an astonishingly improbable state, and probability drives it relentlessly toward the vastly more probable states of higher entropy. And why it started that way? Why we exist in this brief epoch where time has meaning and direction remains the deepest and most shocking mystery Richard Feynman ever confronted. The universe is under no obligation to make sense to us, but in this case, it has given us just enough understanding to glimpse the abyss of what we do not yet know.